Hi, this is going to be a very short video because when I was teaching recording for metric spaces, we have to deal with arbitrary union, arbitrary intersections, etc. And usually such things are never taught carefully. The teachers believe that students had already learned something about union intersection, but they forget it's usually something like finite union at best. A union B, A intersection B, or A1 union A2 union AN. Okay, even countably infinite, they may not have been taught properly. When you learn analysis, you would have learned such things. Possible. Anyway, so this will be a very short video, and I expect that you are all reasonably matured. Final year BSc students are above. Okay, so I'll give some examples, which will also be make sure that you understand the concepts. Okay, let us start. No, it's not yet ready. Just 1 second. Yeah. So let me share the screen now. All right. Okay. So and I would suggest that if you are really serious about mathematics, buy a copy of this. Just okay. It should be less than about 200 rupees. You will learn a lot of things. Unfortunately, these are the things which are expected of you when you go for mathematics, especially the final year BSc onwards. But these things are not taught. Okay. So anyway, let me get started. Let X be a set. As usual, I will assume it's a non-empty set, right? What I want to do is okay. There are two ways of looking at. So I will first do the easy way, which will be a little more concrete. So suppose I is some set, non-empty set. Okay, some set arbitrary. We will call it indexing set. That's why I indexing set or index set. Okay, this is not empty. Okay. What I given, okay, for each I, let me call it for each I am given a subset A of X. So that means, okay, I have a function from I to power set of X. I going to A of I, right? This is a subset of X. Then we denote this I and I. We call this an indexed family of subsets. Subsets in X, of course, indexed by the indexing set I. Okay, let's look at a very easy example. First, if I equal to 1 to n, you know what it means. That is for each one I have A1, A2, AN. That's it. So this is a special case. Okay, this is special case. AI 1 less than equal to I less than equal to n. Okay, this is a special case. In this case, the indexing set is 1 to n. Okay, right. But I may also be able to do for anything. Suppose for a, let my I equal to natural number. Okay, I can think of indexing set. Okay, subset of R. My X may be R. My indexing set may be for each n. Okay, my AN will be minus n to plus n. The open interval or closed interval doesn't matter. Something. Or it could even be Bn. It may be n to infinity. Right? Or Cn, which may be minus infinity to n. So all these families are indexed by naturals. Okay, An. This is indexed by natural numbers. So is Bn, and so is Cn. You understand that? These are called indexed family. But so far, what we dealt with something with numbers. But it's possible I may be able to index it with some arbitrary set. Okay. Let us, for example, just for fun, let's look at. Okay. Now, let C be set of cities in India. Okay. Let S be the set of states in India. States, unitary, union territory, everything. Okay. So all of them I will call as only states, even though legally they may be different. Okay. Then what I can do is for each S in S, I can denote by CS the set of cities in the state. In the state, yes. You understand this? Yeah. This is like your X. Therefore, CS is going to be a subset of C for every S. And you see that the indexing family has nothing to do with numbers or anything. Okay. All right. Let us look at one more thing. Okay. For example, okay. Now let X be equal to R. Okay. And my indexing set, okay, X be equal to R2, my indexing set equal to, let us say, R. Right. Okay. Now I want a subsets for each real number T in I, which is R. I want to define AT, which is a subset of R2. You follow that? Okay. Now my AT is, let us say, that's going to be, okay, put X equal to T. Okay, that is my AT. AT is set of all X comma Y in R2 so that X equal to T. That is this horizontal line. This is my AT. You follow that? Therefore, this family AT is indexed by I, where I equal to R. Okay, I can also define a BT, which is equal to set of all XY in R2 so that X is greater than or equal to T. That in that case, this is my X equal to T, and this is my AT. Sorry, this is my BT. Okay, so we are indexed family, right? Okay. Now, what do I want to do? I want to define, okay, the union of the index family, union of the elements in the index family. Yeah, I and I. So we are in the general case now. Okay, I is an indexing set, X is a subset, A is X is a set, A is are subsets of X for each I. Okay, this is a very general case I am looking at. How do I define? Notice that how do you define union of A and B? It is all elements X, which either are in A or in B. So how do I define A1 union A2 union AN? It is set of all elements X so that X must be in one of the AIs, one of the A1 or A2 or AN. Okay, so you can see there is a quantifier. What is a quantifier? So I can define A1 union AN. Remember, these are all subsets of X. This to be a subset. Any subset is defined by means of not by listing elements, by giving a property when it belongs to that. So when does it belong to? Loosely you will say A belong to one of the A1, A2, AN, but logically you can make it more precise. There exists I in which is set indexing set 1 to n. So that what happens? My X must be in AI. You understand that? Are you sure? Okay. So I'm sure now you can define. So this is a finite thing. So how will I define the general case? I in I. So the notation is union I in I of AI. Okay. This is by definition the union of elements in the indexed family AI. Okay. This is the notation for that. So this equal to what? Now you can mimic. So what do I do? Start with all elements X in X. I have to tell you when it belongs to the union. That is a condition. What is the property? X belongs to the union AI. It belongs to the union AI if exactly the same thing. There is an I in the indexing set I such that X belongs to AI. It may also belong to more than one. I don't care. Do you follow that? Is it easy? Okay. If you just so whenever you define a set, the first thing you should notice is you should ask questions. I give you a Y in X. What does it mean to say Y is in X? Y is in union AI, I in I. What is the meaning? The meaning is there is a J in I. You can also call it I in I. I don't care. so that Y belong to AJ. Okay, you understand that Y belong to union. See, the meaning is this. So when I say Z does not belong to union AI, what does it mean? Look at that. When Y belong to union A, there should at least be one J so that Y belong to AJ. If it is true, what does it mean? You take any I here, okay? Can Z be in AI? No. So what does it mean? That means for every I in I, what I know is that is not in AI. Do you understand this? Pause, review, proceed. See, now we are taking away the intuition, replacing by precise logic. We simply don't say union is okay, the element should be now the subsets. No, we are giving a very precise way so that we can argue carefully. If that is not in the union, that means whatever I take in the indexing set, can Z be in AI? No, it cannot be, because if Z is in AI, it will be in the union according to our definition. So we are okay. Let us look at a very simple-minded example. Okay, let us look at the earlier example where I define 14R. I define AT equal to set of all x, y in R2. My x is equal to R2. Okay, R2. With what condition? My x must be equal to t, right? Okay, you follow that. Okay. Now, what is union of AT? T and I. So you start with an element u comma v in R2. I have to ask the question, when does u comma v belong to AT? When does u comma v belong to AT? U comma v belong to AT if only if there is a t in R, so that u comma v belong to AT. You understand? Next question is, when does u comma v belong to AT? If an element has to be in AT, that means the first coordinate must be t. That means u must be t. Okay, unknown is t now. You understand? Therefore, I found what is t. T must be u. Therefore, when I want to prove u comma v belong to union AT, t in R, I have to find the t, so that u comma v belong to AT. So working backwards, what we found out, if u comma v belong to some AT, that means the first coordinate of this vector u must be equal to t. Therefore, what is my AT? Therefore, take t equal to u, then u comma v belong to AU. Does AU belong to this collection? Of course. This is for any real number. Are you following? Therefore, what do you think I have proved? I have proved union AT, T in R is all of R2. Pause, review, proceed. Before we go further, let us look at some abstract exercises. First, let ATAI be a collection. Let A equal to union AI, I in I. Okay. Now, I want to know, now A is a subset of X. A is also a subset of X, right? What is the nature question I can ask? Okay. Whether A is contained in A. This is obvious question. You understand that? Okay. So when do I say A is contained in A? When do I say A is contained in B? Give me any X in A, I have to show X is in B, right? So let X belong to A. I want to know whether X belong to A. But then if X belong to A, that means there is an I in I. So that X belong to A, that means X belong to union A. That's our definition. You go back. When for X has to be in the union, what should I know? I have to find at least one I so that X is an element of I. So we have proved. Okay, this is very trivial, but I just want you to say how to go through these things rigorously. Okay, right. The next question I can ask is, suppose J is a subset of I. Do you know how to define I is J now. Yes. How do you define? This is set of all x in X, so that there is an I in J, so that x belong to I. See this. If you want, you can also write as I J. I don't care. You follow that. If you don't, if you, yeah, let us look at an example. Okay, the same case A T. Okay, my T was in R and my X was R2. Now let me this. Okay, and T is in R, which is I. My J equal to 0 to infinity. That is non-negative. J is set apart T in R. This is subset, right? T greater than or equal to 0. Now what is union A? What is union? Union A T. T is in J. This is according to our definition. This is set of all xy. So that there is a T in J, so that xy belong to AT. Right? Now start with an element xy. Okay. If it belongs to the union AT here, that means there is a T in J, so that xy belong to AT. If xy belong to AT, when does it happen? This happens only if and only if x equal to T. But what is my assumption about T? T is greater than or equal to 0. Therefore, this means x is greater than or equal to 0. Do you follow that? Xy belong to AT. But what is the T? T is in J. But J consists of only non-negative real numbers. Therefore, my x must be non-negative. You follow that? Therefore, I know union AT, T in J is contained in this set. Is contained in. Okay. This is x greater than or equal to 0 in R2. Is contained in, but is it equal to? I have to prove the other way around. So you start with the point A comma B here with A greater than or equal to 0. Then I want to say A comma B belong to union UT. T is in J. When what T I have to choose? Choose T equal to A. Then AB belong to UA. And this A belong to J because A is greater than or equal to 0. It is here. Yeah. Okay. Please go through, pause, review, proceed. Okay. Let us look at one slightly non-trivial, one more example. This geometric example. Now let x equal to n and my indexing set equal to p, the set of primes in n. Yeah. Now let me define for each p in p. Okay, let me define a to p equals a natural number n, so that n is a multiple of p, or p divides n. That is same as saying p divides n. Right? For example, when p equal to 2, what is ap? All multiples of 2. Therefore, 2, 4, 6, etc. Right? It's very easy. Now notice that if I take 6, 6 belong to A2, it also belong to A3. Because 2 is a prime, 3 is a prime. You understand that? Therefore, it belongs to A2 intersection. So we are not claiming there is only one P. There may be many P, so that my N is in AP. Okay, good. Now my question is, what is AP? So what does it mean? When does a number N belong to this? It belongs to this. That means this implies there is a prime P, so that P divides N, or N is a multiple of P, right? But you know that given any natural number, if it is greater than 1, there always exists a prime, so that P divides N. Therefore, that particular N has to be in that per AP. There is at least one P. You understand that? Therefore, what do I know? Therefore, what do I know is all natural numbers N in N, so that N greater than 1, This is contained in AP, P in P. Are you following? Given any natural number greater than 1, I'm using some fact which you already know. See, this is the important thing. Whenever you have this union intersection, you may have to understand the sets and the properties of the elements, etc. I'm using that. Okay, give me a natural number. When does it belong to union AP? That means there is a prime which divides n. Do I know any fact about this from number theory? Yes. The moment you give a natural number n which is greater than 1, there exists at least one prime which divides p. Therefore, my n will belong to AP. Right? Now, I want to know whether this is equal. So okay, union AP contains all elements of natural number except 1. But can 1 be in any AP? Which is same as saying that there exists a prime p so that 1 belongs to AP? No, because 1 must be a multiple of a prime, so that's not possible. Yeah. Therefore, what is union AP? Okay, right. Let look at one or two more examples. Okay, an abstract example. Suppose X is a set, right, and B is a subset of X, right. Suppose for each X in B, okay, I am given a subset AX of X, so that X also belong to AX, and AX is contained in B. You understand this? So I have X. Okay, you give me any X, then so this, let us say this is my B. Okay, then I have an AX. This is my AX, and AX contains X and contains this. So if you give me some other thing, this is my X. This is my AX, and that is contained in B. You understand? Now my question is, so I have index family AX, X and B. What is the union? This is what we used for when we dealt with open sets, etc. That's very clear. Notice that AX is always a subset of B, therefore this is a subset of B. Right? Okay. Next. Now start with any Z in B. Right? By my assumption, for every X in B, there exists AX such that X belongs to AX and AX is contained in B. Therefore, for this Z also, there exists AZ. With what property? Z belongs to AZ and AZ is contained in B. You understand that? Okay. Therefore, AZ belongs to the family AX, X in B. Right? You follow that? Okay. Therefore, my Z belongs to the union AX, X in B because Z belongs to AZ. I have to find an X so that Z belongs to AX. But what is the X I am taking? Namely Z. Do you follow that? When you learn union of open sets is open, etc., this is the kind of argument we used in matrix spaces. Okay. And there is two more examples I will give. Few more examples. Okay. Let X equal to R2. Okay. CR equal to set of all XY in R2 so that X squared plus Y squared equal to R squared. Okay. You understand that? Okay. Now suppose my R is the interval, closed interval 1 to 4 in instance of R. This is my indexing set. Sorry, this is the indexing set. Okay. So what is CR? CR is a circle of radius R centered at origin. This is my CR and this is R. Right? You understood that? Okay. This is my indexing set. Oh, maybe I should do it to 1 to 2. Therefore, it's 1 to 2. Yeah, CR. Okay. Therefore, what is union CR? CR and I. So this union of all circles where radius 1 up to radius 2. You understand that? My R is going to be an I. Yeah. So this is a, let's say, circle of radius 1 and this is a circle of radius 2. Okay. This is 1, let us say 1, and this is 2. Then all these circles will be, that means this is an annular region. You understand? And both the boundary circles are also included. This is C1, that is C2, both are included. Do you understand that? Okay. So one slightly abstract example again. Let us look at x equal to m n m2r, that is 2 by 2 real matrices with entities in C, entities in R, right? Okay. For any C, a real now, my I equal to R. You understand that? Okay. Now what I am doing, for any C in I, that is C in R, I define a subset AC is set of all, maybe I will denote by some other name, YC. Set of all matrices A in 2 by 2 matrices, so that determinant of A equal to C. So I have index family YC, C is in R. This is a subset of matrices. Now let me take J equal to R minus singleton 0. That is all non-zero reals. So what is union of YC? C is in J. So so start with a matrix A in M2R. Okay, when does it A belong to the union? If and only if there is a C in J. That means a real number C not equal to 0, so that determinant of A equal to C. In particular, determinant A is non-zero, right? So what is the conclusion? Therefore, you can see union YC, C is in J. Now you should, again, you will understand what I said earlier. Okay, the subsets, the properties are elements in the subset. Okay, you should understand. The moment you think a matrix is such that the determinant is non-zero, what do you think of? It is invertible, it's non-singular, right? Therefore, if A belongs to union YC, then this is a subset of set of invertible matrices or non-singular matrices. Matrices in M2R. Yeah. Now I want to know whether it is equal. But that's very easy. Suppose B is a matrix, thus the determinant of B is not equal to 0. Call this as C or B. Okay. Then B is not equal to 0. Then my capital B belong to Y of B. And B belong to J. That means B belong to this. You understand? Therefore equality holds. Okay. I think now more than enough. Let us look at arbitrary intersections. The same notation. AI, okay, I and I, index family. I want to define AI, I and I. This is what is known as intersection of the index of elements in the index family. So now I think you should be easy. How do I define A1 intersection A2 intersection AN? It is set of all x in X with what property? X belong to A1, X belong to A2, X belong to AN. How will I write it? For every I in 1 to N, my X belong to A. This must happen. Then only this, right? So how will I define this? So I will define this is set of all x in X, so that for every I in I, okay, we have X belong to AI. That is, X must be belong to each and every AI. That is loosely saying that we are doing. Therefore, if I say a Z is not here, what does it mean? So z is an element of x. I say z is not here. What does it mean? See, that is where the logic is needed. If it is there, for every I, x must be in I. So this is false. What does it mean? Therefore, z does not belong to intersection I if there exists a j in I, so that x is not in age. At least it does not belong to one of the elements. Okay? Do you understand? Right. Okay. So now what is the relation between A intersection B and A union B? Or A1 intersection A2 intersection AN and A1 union A2 union AN? This contains each and every element which is at least in one of the A's. This contains only those elements which are in every A. So intuitively it's very clear there. This is a subset of this. So here also we want to prove the same thing. What is that I want to prove? Intersection I in I is a subset of union I in I. Right? But remember, we are going to make use of the fact I is non-empty. Do you remember I said that my indexing set is non-empty? So let x belong to intersection I in I. What does that mean? That means there is a j in I so that x belong to, or if you want to make it I, x belong to I. But if there is an I such that x belong to I, this implies x belong to union I. You see that? We use the fact I is non-empty here. Okay? So you can think of examples like this again. Okay. I suggest that you go to the book, try to buy it. Okay. Or if it's available in your library, please check it. Okay. Before I end the lecture, there is slightly uh, different concept, but which is exactly similar is the following. Suppose X is a set. Okay. I simply say A is a collection of subsets. That is, A is a collection of the power set. I want to talk about union of elements in A. See, now there is no indexing or anything. You understand that? What should be? So I will simply denote it by A and A. Don't think of this indexing set, it is just this. Okay, this is a notation. Okay, how do I read it? It's a union of elements in the family of subsets. Is the family indexed? No, I do not know. It's not indexed. Then how do I define? I'm sure all of you by now know. There is the set of all x in x so that there exists A in the family script A so that x belongs to A. That's it. So it's as good as saying it is indexed by script A. Do you understand? And similarly, intersection A in script A. See, the only thing is it may not be indexed. That's why I have to say x belong to x so that for every subset A in script A, x must be an element of A. Okay. Right. Because in you will see in topology and analysis, you will have to work with this kind of thing, which is not necessarily indexed family. Okay. But still we can talk about. Okay. For example, in the definition of topology or in the metric space topology, what you will say? Okay. If U is a collection of open sets, then the union of elements in U is again open set. Okay. Now you see that this is just a collection of subsets. So I have to talk about the union. How do I do that? This is the way. Yeah. Okay. Please go through. There is a lot more I can do, but this is, as I said, I wanted to be a short video, and so that okay, this will give you enough material for you to follow topology course or metric spaces course. Okay. I hope you enjoyed. Have a good day. We will stop. Yeah. Before we sign off, let us prove one example. Let us look at an example. and also prove a result which is an obvious result, right? So as a kind of example for just 1 second, I have to yeah. So let us look at x equal to r, right? And for every epsilon positive, let my set a epsilon be the set minus epsilon to plus epsilon. You understand that? Okay. Now I want to know what is intersection a epsilon. Okay. What is my indexing set? Indexing set is set of all real numbers epsilon and r such that epsilon is positive. Okay. So I want to know what it is. Right? Okay. First notice that when does x belong to epsilon? Of course, you can say x lies between minus epsilon and plus epsilon, but there is also another way of saying if and only if mod x is less than epsilon. You understand that? Therefore, there is an obvious guess. You know that 0 belong to that. Do you understand that? Because 0 belong to each and everything, right? Now, suppose I have a real number t which belongs to intersection a epsilon, epsilon in I, which is same as saying you can write like this. Okay, what is this? This says that mod t is less than epsilon for every epsilon positive, right? T belong to all a epsilon. That means given any positive epsilon, mod t must be less than epsilon, right? So what is your guess? You would like to say then mod t must be 0 and hence t is 0, right? How do I prove that? See, this is where I said the knowledge about the set, subsets, and the elements of the set, they all matter if you want to conclude something about the union or intersection. Okay? Because set theoretically, we define what is intersection, what is the union, but I want to identify what is the intersection and what is the union. In that case, in the intimate knowledge about the set, their subsets, the elements may be of use. This is an example. Okay. Now let us look at I suppose mod t is positive, right? Therefore, if I take epsilon equal to mod t by 2, this is also positive. And according to me, t is in this particular a epsilon, where epsilon is like this, right? So what does that mean? Mod t should be less than epsilon. But what is epsilon? Mod t by 2. That's a contradiction, right? Hence, we conclude mod t must be 0, that is t is 0. Therefore, intersection a epsilon, epsilon positive is singleton 0. Is it okay? Just the same thing, but I will change the indexing sets differently now. Okay, my x is equal to r. My now I will define an to be minus 1 upon n to plus 1 upon n. My indexing set I is natural numbers. This you must have seen in nested interval theorem. Okay, this is the first counter example they will give you. Okay, now I want to know what is an n. So again I know 0 belong to that. Suppose t belong to intersection an and n in n. Okay, usually teachers will write 1 to infinity an, but this is a much better way of writing. Okay, what does that mean? So that means mod t is less than 1 by n for all n, right? Now again you can see what I want to say. Now where are we? The x's, real numbers, natural numbers, and integers, and I'm looking for a real number t so that mod t is always less than 1 by n. Now I have to know intimate knowledge about real number system. Then I know what it is. By Archimedean property, suppose this is mod t, I I want to claim this. Okay, suppose false. Therefore, mod t is greater than 0. If it is false, mod t is greater than 0, right? By Archimedean property, there exists a natural number n so that n times mod t is greater than 1. Yes, you understand this? Right, what does that say? That says mod t is greater than 1 by n. You follow that? But therefore, this implies t is not in a capital N. Because if t is in a capital N, mod t should be less than 1 by n. Whereas this one, okay. If t is not in n by n, that implies t is not in the intersection. Because it should be in a n for every n. You understand? Therefore, this is a contradiction. Therefore, what we conclude? Intersection an, n in n is again singleton 0. But to prove that, what did we need? We need Archimedean property. In the earlier case, what did we need? If epsilon mod t is positive, then mod t by 2, that is also positive. These facts we needed to prove that. Okay, right. So the last result, with that we will stop, is the following. All right. So you know what is De Morgan's laws, right? A union B, its complement is A complement intersection B complement, etc. Okay, we will prove now them. Suppose I have a set X and I and I is index family. Okay, I am just using index family, but remember you can also use without index. Okay, for convenience sake, for understanding sake, I am assuming there is an index. Okay, right. Okay, now I want to know, suppose A, the union, and what is its complement? What is this by definition? This is X minus union AI, I in I. Okay, this is a complement. Okay, let us understand. Now, X in union A and its complement is same as saying X is not in union A. You understand this? I in I. I'm not writing I in I, but if you want, you should write that. Yeah? Right. What does this mean? This means I claim for every I, yeah, X is not in A. Do you accept it? Because if for some J, X is in AJ, then it will be in the union. Therefore, X is not in the union if only if X is not in any one of the A's, right? Maybe it will be easier for you to think of it that way. X is not in the union means X is not in any of the A's. Even if it is in one single A, it will be in the union. You follow that? But what does this mean? This means for every I in I, X belong to A complement, right? What does this mean? For every I, X belong to A complement. That means X belong to A complement I in I. This is the intersection, right? When does X belong to that? If and only if X belong to each of the set. We have proved it. So what do you think I have proved? So we have proved the result. I in I and AI, its complement is intersection AI complement I in C. I in I. Right? And similarly, intersection also you can see. Okay? It's exactly similar proof, but you should try on your own. Okay? And these are the enough thing. These are, I hope these are all enough for you to go through various things. Remember, as I said, okay, very rarely teachers take, pains to explain these things. You will talk about compactness, open cover, admits of finite subcover. You don't even understand what is open cover. And similarly in the topology, you will see union of sets, open sets is open, but you have to learn such things. And that's and my experience tells me even MSc students have problem. They only know how to work with finite collection. So that's the reason. I hope you enjoy. Thank you very much. And go back to my lectures on metric space and topology. Bye.